Welcome everyone to section number 4. In this video, as promised, I'm going to tell you the derivatives of our favorite trigonometric functions, and better yet, we're going to prove why the derivative is the way it is. So you don't even have to take my word for it. So we'll prove some trig derivatives, and then we're going to apply these to actually get some formulas for some other trig functions. Okay, so the big theorem here, Theorem 4.1, is that the derivative of sine of x is equal to cosine of x. And likewise, the derivative of cosine of x is not actually sine, but it's actually negative sine of x. And so before I get into the proof, right, I'm going to prove this part A right here. Before I get into the proof, let's go ahead and bring up our good old Desmos graph here. And we can see that, right, if I have my function sine, and if I go ahead and map the derivative, right, the slope at a bunch of points. So here you can see the slope's positive, so I've mapped that positive value here as the y-coordinate. And as I go ahead and I'll just hit play here, you can see that this derivative kind of moves back and forth similar to sine. And in fact, if I go ahead and show you, here's the function that the derivative follows. Then I can go ahead and map y equals cosine of x, and you can see that this exactly matches up with the derivative of sine. So this is a nice visualization of, right, the derivative of sine being cosine. Now let's go ahead and do the nitty-gritty, the formal math proof of this thing. So I'm going to formally prove it, but in order to prove this, I need to remember a geometric, or really a trigonometric fact. So let's go ahead and say recall, and I need to know the angle addition formula for sine. So sine of A plus B. So if I add these two angles, A and B together, can I calculate out the sine value of this? And so this was relatively complicated. So this was sine of A times cosine of B plus sine of B times cosine of A. And that is the angle addition formula for sine. With this, the claim is I can go ahead and get pretty far into my proof. So again, I want to do the derivative of sine of x. Well, I don't know any rules or tricks or ways to evaluate this, and so I need to fall back on my definition of my derivative. So this is going to be a limit as h goes to 0 of sine of x plus h minus sine of x all divided by h. So that is the definition of the derivative. And now notice I have a sine of x plus h. I want to go ahead and use the angle addition formula on this. So we'll have the limit as h goes to 0. And now you can think of all of my a's here, I'm going to use x's, and all of my b's, I'm going to use h's. So I'm going to have sine of x cosine of h plus sine of h times cosine of x. So that's all this bit minus sine of x all divided by h. All right, so at this point I want to do a little bit of grouping. I want to group together all of the things that have sine of x's and everything that doesn't. So maybe let me go ahead and rewrite this really quick. I'm dividing all of this by h. So let me go ahead and break this up, divide the first bit by h, divide the second bit by h, and the third bit by h. Just kind of breaking up our denominator there. And again, I'm going to group together all the bits with sine of x. So here, this one has a sine of x, this one has a sine of x. And notice they all are divided by h as well. So if I go ahead, everything that has a sine of x, I'm going to group together. And I'm going to go ahead and factor out the sine of x. So if I factor out the sine of x from this first one, I'm going to have cosine of h. And let's see, This one, if I factored out the sine of x, I'm going to have minus 1. And both of these are divided by h. So I'm going to go ahead and divide this by h here. And now the stuff that doesn't have a sine of x, this one right here, I'm going to go ahead and write this with the cosine out in front, and then sine of h over h. So notice the thing here that's changing is h is going to 0. The x's aren't changing at all, right? These are basically constants. So I can go ahead and factor these out, and let me distribute this limit. This is going to be sine of x times the limit as h goes to 0 of cosine of h minus 1 over h plus cosine of x times the limit as h goes to 0 of sine of h over h. Right? So I can't take anything with an h outside of this limit, but I can take anything with an x. So that's how I was able to factor out this sine of x and this cosine of x. So now the big question that I have remaining is, what does this limit evaluate out to? And what does this limit evaluate out to? And in fact, we've already seen that we know the answer, that it evaluates out to just cosine of x, right? So this bit goes away. In order to make this going away, right, it's nifty to be able to multiply by 0, perhaps. So this one we hope is 0. And then this is just positive cosine, so I'm hoping that this evaluates out to 1. Now that is my hope, and the claim is I need to prove this still in order to make this cosine of x. But for right now, I would like you to take my word that these are true, and actually in our second video, we will deal with trig limits, and we will show that these two limits hold true. But this kind of, it sets up the motivation. Why are we interested? In particular, this one right here, the limit as h goes to 0 of sine of h over h. We will do lots of problems like this, and this sets up why we are interested in that limit. Because in order to calculate out the rate of change, right, the derivative for sine, we need to know how to evaluate this limit. And if you try kind of any of our techniques from 1.6, right, if you plug in h equals 0, you'll get 0 over 0, but you can't multiply by a conjugate, you can't get common denominators, right? We don't have a way to evaluate this out yet. And so, again, that'll be our second video here in section number 4. All right. And so again, once we see these limits actually are what I'm telling you they are, right, we'll have the formal proof why the derivative of sine is equal to cosine. And likewise, you could prove that the derivative of cosine is equal to negative sine. Again, you would need to have the angle addition formula then for cosine, but you would be able to prove this. All right, let's go ahead then and apply this to a few problems. And we're going to go ahead and get the derivative formulas for some other trigonometric functions. So that's really going to be our applications here, is that I would like to be able to take the derivative of tangent. And okay, these first two we want to put to memory. We're going to use these ones a lot in this course. And then I have these second two here are extra. You should be able to calculate these out on your own, but I don't need you to necessarily memorize them, right? So these first couple, I really want you to memorize them and have them, at your fingertips, ready to use whenever you need. All right, so the first one, the derivative of tangent. Well, I know that tangent I can go ahead and rewrite as sine over cosine. So this is going to be the derivative of sine over cosine. And since we know the derivative of sine and we know the derivative of cosine, the claim is all we need is the quotient rule, right, from section number 3, and we'll be able to calculate out the derivative of tangent. All right, so the derivative of tangent, right, quotient rule time. It goes low d high, so low d high. So the derivative of the high function, the numerator function, so the derivative of sine is cosine, minus high d low, high d low. So the derivative of the low function, well, derivative of cosine we learned was negative sine, all divided by the bottom squared, or all divided by the low squared, right? So this is going to be cosine of x squared. And so we can actually simplify this a little bit, right? We can see this negative and negative makes positive, and we can write this as cosine squared x plus sine squared x over cosine squared x. And maybe this cosine squared plus sine squared, triggers something from, your good old trig days, that there's a way to simplify this down. So cosine squared plus sine squared, turns out one of our identities says that this is equal to 1, no matter what x is. So here is the derivative of tangent, fully simplified, right? 1 over cosine squared. Now in lots of textbooks and in formula sheets and stuff like this, you will quite often see this written as secant squared, right? Because 1 over cosine is secant. So therefore 1 over cosine squared will be secant squared. So this is the derivative of tangent. And again, I want you to put this to memory, right? You should have very quickly, if I ask you, what is the derivative of tangent? You should be ready to fire back, right? It's secant squared. All right, likewise, let's go ahead and take the derivative of secant. So remember secant, well, this is going to be 1 over cosine. 1 over cosine. All right, so again, we really see a quotient of two functions. So I'm going to go ahead and apply the quotient rule to this. So, okay, we have low d high, so cosine, times the derivative of the high function, right, the numerator function. Well, the derivative of 1 is 0. All right, that's nice. Minus high d low, the derivative of cosine is negative sine, divided by low squared. I'll just go ahead and write cosine squared x. All right, so 0 times anything is 0. And then we have this negative and this negative, so that's going to be positive. Sine of x over cosine squared x. And this right here is personally, how I would probably leave it. But again, in most textbooks and on formula sheets and stuff like this, they go ahead and break it up and they say this is sine of x over cosine of x times 1 over cosine of x. And therefore they write it, right? Sine of x over cosine of x is tangent. And 1 over cosine of x is secant. So you probably will see that the derivative of secant is tangent secant. So again, I want you to have this memorized. All right. But you can see, right, if you forget these things, well, you can rederive them, right? So if you get stuck on a quiz or an exam or something like this, and you need to know what's the derivative of tangent, and you forget, right, you can always rederive it thanks to the quotient rule. Okay, so these ones that you don't have to put to memory, but again, you should know how to figure out their derivatives if you're asked. So the derivative of cosecant. Well, remember, cosecant is the same thing as 1 over sine. Just like secant is 1 over cosine, cosecant is 1 over sine. So again, this looks awfully quotient rule-y, right? So I'm going to, again, get lots of practice with the quotient rule today. So I'm going to go ahead and evaluate this using the quotient rule. So we're going to have low d high, and the derivative of 1, again, is 0, minus high d low, so the derivative of sine is cosine, all divided by low squared. Let me go ahead and simplify this, right? Anything times 0 is 0, and so I'm going to have minus cosine of x divided by sine squared x. And if you were deriving this again, this is just how I would leave it. However, you will see in some textbooks, you'll have something like negative cosine of x divided by sine of x times 1 over sine of x. And so you can express this as negative. Now cosine over sine is cotangent. And 1 over sine, well, that was cosecant. And so you can see, actually, the derivative of secant and the derivative of cosecant, right, B and C, are actually friends, right? Basically, with this co here, right, instead of tangent, you get cotangent. Instead of secant, you get cosecant, right? They're friends, but then you also have this extra negative sign. So you do have to be a little bit careful with that. All right, but they're certainly related to each other. And likewise, as you would probably guess, cotangent is somehow friends with tangent. right? So if you take the derivative of tangent, you get secant squared. If I was guessing, it'd be something maybe like cosecant squared. Let's check though and make sure that we're not off. So okay, let's go ahead and write this. The derivative of, instead of cotangent, let me write cosine over sine. And again, using the good old quotient rule, we're going to have low d high, and the derivative of cosine is negative sine, minus high d low, and the derivative of sine is cosine, all divided by low squared. Okay, let's go ahead and rewrite this. Notice that both of the terms in the numerator have a negative sign. So I'm going to go ahead and factor out that negative sign. And when I do that, this first one becomes sine squared. And the second one becomes cosine squared. So when you factor out the negative from each one of these terms, you get your sine squared plus cosine squared. And we've already seen that this is an identity, right? That we can go ahead and replace that with 1. So in this case, we're going to have negative times 1. That's going to be negative 1 over sine squared. And, well, 1 over sine is cosecant. So this is going to be cosecant squared. But then don't forget about this negative sign. So again, if you look up in a textbook or something like this, you'll find that the derivative of cotangent is negative cosecant squared. And so you can see that this is, again, friends with tangent. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared. But you have to remember this negative sign. All right, that is the end of this first video where we see that we can take the derivative of lots of trigonometric functions now. The only thing that's kind of left is, well, we want to be able to kind of more formally do these limits with trigonometric functions. So that's going to be our second video here, doing trig limits. I'll see you next time.